Welcome to Get Your FRQ On. This question is from 2012. It's question 2, and it is calculator active. In the question stem, we have a region in quadrant 1, bounded between the graphs of two functions and the x-axis. In part A of the question, we are asked to find the area of the region R. Now, one of the things we have to do before we can find this area is we have to figure out where these two graphs intersect, because that point of intersection is not provided to us, and the upper function that we need to integrate with changes wherever they intersect. So this is a calculator active question. We need to determine the x value where these two functions intersect so that we can use that appropriately as the bounds for our integrals. All right, so it's a calculator active question. Use your calculator to figure out the solution to the equation natural log of x equals 5 minus x. If we do that, we find that the two graphs intersect at 3.6934414 and y equals 1.3065586. Notice the extra precision here. The reason we're going to do this is we're going to have to use this to integrate with our calculator. And if we round these values to 3 decimal places, the integral we get will likely not be accurate to 3 decimal places, as is the expectation. So when you're using a decimal in a problem like this, you typically want to use extra precision to make sure that when your calculator is doing math with that decimal, you can still get your final answer to be correct within 3 decimal places. Be that as it may, the x value we need is 3.6934414. We're going to call that s. This way we don't have to keep typing it out or writing it out if you're doing these problems by hand. But that means that the area of the region R can be found by adding these two integrals together. If I integrate the natural log function from 1 to s dx, and I add that to the integral from s to 5 of 5 minus x dx, that sum is the area of region R. Now, to calculate this, again, this is a calculator active question, let your calculator do the work. The sum of those two integrals is about 2.986. In part B of this question, we are told that R is the base of a solid, and that cross sections taken perpendicular to the x-axis are squares, and we are asked to write an integral that would find the volume of this solid R. Note, we do not need to evaluate the integral. We are not finding the volume of the solid. We are writing an integral that would find the volume of the solid. Right. Since cross sections taken perpendicular to the x-axis are squares, the area of each one of those squares is going to depend on where we are relative to this number s that we found in part A. So this is going to be written as the sum of two integrals. You don't have to, but it's probably easier that way. So the volume of the solid would be the integral from 1 to s of natural log of x squared dx. That integral is finding the volume from 1 to s. Keep in mind, these cross sections are squares no matter where we're at, so it doesn't, the square doesn't matter on where we are relative to s, but the function we're using does. So we have that integral plus the integral from s to 5 of 5 minus x squared dx. All right, we don't have to evaluate this, so we're not going to, although we could with a calculator. We just need to write that integral. In part C, we are told that the horizontal line y equals k divides the region R into two equal areas, and we are asked to write an integral to find the value of k. So because the line y equals k is horizontal, it's going to be easier to write this integral if we integrate with respect to y instead of x. In fact, probably necessary. So what this is going to mean is we're going to have to take our boundary functions, which are functions of x, and rewrite them as functions of y. right? So if we have the boundary function y equals natural log of x, the inverse of that is x equals e to the y. And if we have the boundary function y equals 5 minus x, the inverse of that is x equals 5 minus y. And then notice that if we're integrating with respect to y, the area of this region doesn't change just because we're integrating with respect to y. So I can write the integral that I could use to find k by integrating from 0 to k, 5 minus y minus e to the y dy equals 0.5 times the area of r, which we already found in an earlier part of this question to be 2.986. So here I have an integral that's technically an equation, and if I'm solving for k here, that solution would be the desired value of k.